Okay, in this example, we're supposed to state all the real cube roots of 125. Now, what the real cube roots of 125 is referring to is what number to the third raised to the third power will give us 125. That's what that question poses. So here I have a list of a bunch of the perfect powers, and we're just going to use that idea. We're looking at the third power because we're doing the third root. If I look down the column for 125, here is 125. So I know that 5 to the third power is 125. So the answer is just that x is going to be 5, or that mystery number that we're looking for is 5. Now, however, with the second example here, we're asked what are all the real fourth roots of 16? Well, that's a little bit different. So if we go through the same motions, x to the fourth equals 16, we can still find 16 on this table. I see it here, but this is underneath the square root column. We want the fourth root, the fourth power column, so here we are, and there's 16. So 2 would be the answer, though there is something that we are neglecting. Earlier in the year, we did square roots, solving equations like x squared equals 16 with reverse order of operations. And we had to add the plus minus sign as we were solving those equations because there were two possibilities. Well, that's true for here as well, because both 2 to the fourth power is equal to 16, but in addition to that, negative 2 to the fourth power is also positive 16. So in addition to positive 2, we also have x equal to negative 2 as a possibility. That's not the case, however, for odd exponents or odd roots like the first problem, because if we try that here, 5 to the third power would be a positive 125. However, negative 5 to the third is actually negative 125. So if it's an odd root, then there's only going to be one answer, but even roots or even exponents there will have the positive and negative if we're talking about real roots. In this example, we're just going to be talking about the meaning of these rational exponents or these fractional exponents. Now, a fractional exponent is just a way of combining both a radical and an exponent at the same time. So the top number in a fractional or rational exponent represents the actual exponent with the variable or number, while the bottom is the index or the root that we're talking about. Index being the small number on the outside of the root. So if we're talking about 16th to the 1/4 power, then we can rewrite this as the fourth root of 16 to the first, or as an alternative way, the fourth root of 16 in parentheses to the first. Now the 1 here in this case is not implied, I'm just emphasizing it for the interpretation of the meaning. The second one here is 27 to the 2/3 power, the top number being the exponent, the bottom number being the index, or the root. So we would have the third root of 27 squared, or we can write it as this way, of the third root of 27 in parentheses squared. So either way works. Depending on what you're doing with it, one interpretation might be a little bit more useful than the other. Okay, in this example, we're going to be evaluating 3 expressions. So I'm going to give myself a little bit of space for each of the expressions. We have 32 to the 3/2 power, 27 to the negative 2/3 power, and 50 to the 3/4 power. Now typically, Evaluate will mean just to find the value of an expression. Decimals, fractions, and stuff are usually okay, but we are going to be restricting ourselves to not be using decimals. This way we can experiment with the properties that we're discussing in this lesson. So for this first one, 32 to the 3 seconds power, we are going to first change this into the radical form. So we have a 2 as the bottom number, so that's going to be the index. And 32. And for most of our problems, when we're trying to evaluate rational exponents, most of the time this form is more helpful, at least for the scope of what Algebra 2 is concerned. So we have the square root of 32. That's not the square root, that's the fifth root. I wrote it wrong. Fifth root of 32. Ooh, I was wondering there because I knew they were all supposed to be perfect powers. So the fifth root of 32, if I pull up the chart, you can see the fifth root of 32 is right here. It is 2. So fifth root of 32 is 2. And then we're doing 2 to the third power, which is 8. So that's the first one. It just involves switching it to a radical and then evaluating it from there. Same thing with the second one, though this one has a negative exponent. A lot of people misunderstand what negative exponents mean. They do not mean make the number negative. Instead, they mean to move the number that has the exponent to the opposite part of a fraction. It means reciprocal. So we're going to turn this into 1 over 27 to the positive 2/3 power. It's an exponent property that should have been done earlier, probably in Algebra 1. The specific property is a to the negative n power equals 1 over a to the n, assuming that a is not 0. With that being done, it follows the same way as the previous one, where we turn it into a radical form. So 1 over, the bottom number is 3, so that it's going to be the third root of 27, and the second power of that. Now the third root of 27 is 3, so we have 1 over 3 squared, and 3 squared is 9. So overall, it's 1 over 9. And you can always try typing in the calculator as well. If you did type in the calculator as the original thing, you should get 0.11111 repeated. Now if we go and look at this last one, as we go through it, we see the bottom number is a 4. So we'll do the fourth root of 50 to the third power, like so. However, if we check out our fourth roots, you can see here's the fourth root column. 50, well 50 is not here. 50 would be between the 16 and the 81 if it was a fourth root, but it's not a fourth root, so we can't actually do anything with this. So in this case, because we can't break down the 50, turning it into the fourth root of 50 to the third power is typically the better option. And then we can actually do the fourth root of 50, or 50 to the third, I mean, which is not an ideal number. It'd be 125,000. Now, from here, you can actually break it down. At least I believe we can. Yep, I do believe you could simplify the radical, but that's not really our purpose for today. So this could be simplified because we can get a fourth root out, but as far as evaluating, we can't get a specific exact answer. So that's where we're going to leave it for today, but we will continue looking at situations like this further.